Hello, I'm Dr. Chris Parker, and today we're going to be calculating sample size. Sample size is an incredibly important concept because if your sample is too small, then you cannot run your test. Now, let's go through this a little bit. Now, parametric statistics, such as t-tests that use normal curves, they rely on the means, the averages. Now, if there's 10 people in a room who all work in a standard job, and then Jeff Bezos from Amazon walks in, who's a multi-billionaire, the average in the room has completely gone up. So everyone's a multi-millionaire, or multi-billionaire maybe. So you need to have enough people to have a good sample. How big is that is a question lots of students ask when they're learning stats, and there's no single answer, but the best way of doing it is calculating the right sample size. And this is something that mathematicians get wrong in top leading journals. There are Nature journals, which is the best journal in the world, publishing papers without power calculations. So if you get this right, you're at the top of your game straight away. So why is sample size important? Well, power is this measure which is the confidence we have that our calculations are true, that our results are true. If you have a small sample size, you have a small power, and you may get a significant result, but probably isn't correct. Let's give you an example of this from an academic journal. This is a paper by Dr. Bem called Feeling the Future. Now, in this paper, Dr. Bem proved that future actions influence our past. Think about that. That's time travel. So he showed that you get two groups of people and give them a series of blank cards. Show them. And ask people if there's a picture on the other side, yes or no. After the experiment, the group was shown the cards. One group was shown the cards and revealed which ones had images on. To make sure they really noticed them, these were porn images, so really erotic items. And the group that was shown the pictures on the back of the cards after the guessing game had a significantly higher guess rate. Now, that is wonderful. It means that time travel is possible. There's things that the things we do now influence things in the past. That's incredible. And impossible. It's crap. And he achieved a power of 0.89, which is an 8.9% chance that he is right and a 91.1 chance that he's wrong. Dr. Bem did not get a good enough sample size to get the results that he gave. Now, sometimes people play down power because power is really important when it is life and death medical research things, but what about design? Who cares about design? It's just a front page website. No, it's not just the front page of a website because you might have two designs that are very different and run a satisfaction score. Design 2 might score higher, significantly higher, and the management go, well, that's it. We're never doing design 1 ever again, and kills the idea, whatever it is. And if your sample size is too small, your power is too small, maybe you got the wrong answer. Maybe if you had the right sample size or the right power, site 1 would have been higher. So power is the confidence. If you get your power right, then you are doing really well. Now, it also affects the kind of test that you're running. Now, I said about the averages at the start and Jeff Bezos influencing scores, because Jeff Bezos walking into a pub, everyone's multi-millionaire in the pub because you're taking the average wage. That's not very good. So really, really simple thing is you run your basic stats is running your Colonel-Smale test, work out if you have normal data or not. Non-normal data is non-parametric. Normal data is parametric. But we can add another layer to this, and this is, firstly, yes, run your Colonel-Smale test. Are you significant? Yes. Non-parametric? No. Parametric. But before we go to parametric, we ask ourselves, are we achieving a power of 0.08 with our sample or higher? If yes, carry on with parametrics. If no, if we're achieving a power below 0.8, then we go over to non-parametrics. And that is a good way of working because it makes sure that the tests we have are appropriate. So how do we go and calculate that power, and how do we predict sample size? So predicting sample size, use software called G*Power. Now, G*Power is free. It does a lot of stuff that I'm not going to go into in this video, but you can achieve sample size that you require for your test, and you can do the power that's achieved. So here's an example of using a dependent. So in this case, we say it's the t-test family. We're doing the means matching, the means difference between two dependent means, match pairs. And the test we're doing is a priori. A priori is just, we're planning our test. How many people will we need? So we go to the parameters and we say we want two tails. The effect size we're looking for is a medium, so 0.05. And that means that as long as we get a medium effect size, our results are good. The alpha, 0.05, as standard, unless you're doing a bump-for-only adjustment, as I talked about in my previous videos. And the power I want to achieve is 0.8. The reason it's 0.8 is just an agreed upon number, nothing magical about it, but statisticians get very happy when they see 0.8 power and very sad when it's below. So just take it as that. When you're running an independent, it's very similar, but we're going to be choosing a different test. It's the between groups 2 independent means, so 2 groups. Still an a priori, we're still using a two tails, still using effect size of 0.5 medium, still using an alpha of 0.05, and still using a power of 0.8. What's different with the independent is that we're going to have allocation ratio between the groups. So because we're using different size groups, there's going to be a ratio. Now, if we add 20 in group 1 and 10 in group 2, that's 2-to-1 ratio, or 2. If we got 20 in each, it's 1. So it's a very simple calculation of group 2 divided by group 1 for sample size. And you get that. So we work out that for a t-test independent, for a medium effect size, you're going to want around 128 people. And if you're running a dependent, you can run about 34. So it really depends what kind of t-test you're running on the sample size. It's not good enough to just say 100 people's right. It depends what you're doing. And of course, if you're looking for a smaller sample size, if you're looking for a smaller effect size, if you're looking for using a bump-for-only adjustment, so a lower alpha, or maybe you want to have more confidence in your results, so a higher power, that will affect the numbers up and down. Now, you do this at the start of your methods. When you're planning your methods, I want to use a t-test. How many people do I have to recruit? So for dependent, maybe 34, independent, maybe 128. That means you're doing it right from the start. It doesn't guarantee that you will achieve the right power. So what we're going to do now is run through and check achieve power. Let's start with a t-test. We calculated in previous videos that a dependent means t-test gave these results. I won't go through them all, but you can pause the video now if you want to read this. The important things are the numbers in pink. So I open up G*Power, and again, t-test family. The test is dependent means match pairs, and it's a post hoc. Post hoc is after the experiment. So parameters to put into is 2 tails. Now, the next part, degrees of freedom. Previously, we said, give me 0.5 because that's a medium size. But this time we're actually going to calculate it. And you click on the calculate button and you see that there is a drawer that pops out. You choose to add the mean standard deviations, which you got from your results previously. You put them in there. There's one piece missing on that, which is correlation between groups, which I'll go on to in a second. Then the alpha is the alpha you achieved. Sample size is the people in your sample. So that's all relatively simple, apart from that one correlation part. Now, once you put all those bits in the drawer on the side in, you press calculate and then transfer to drawer. That puts the actual effect size you had into there. Now you might say that you already calculated the effect size. There's different ways you can calculate effect sizes. The measure which G-star Power used is different to what I showed you, which is why you should use the draw on the pop-out. Now how to calculate the correlation is very simple. It's in Excel, correl, open bracket, select array 1, which is the first set of results, then comma, then select the second set of results, array 2, and that gives you your correlation. In this case, it's 0.04, so that's a relatively simple test to do. Let's go and do this for t-test. Again, we worked out all our parameters from the previous videos. I'm not going to go through it. Here we are in G-star Power. Again, it's t-test, it's means difference between independent means, and we're looking at a post hoc. And post hoc, again, is after the experiment, two-tail, and then the D, we slide the draw out, you put our means in, put our standard deviations in, calculate, push transverse draw, and it pops across. In this case, we got 2.74 for the effect size D. Alpha, achieved alpha. The group size, really simple, it's same as both groups, and we are good. Now that gives us the independent, and off we go.